Our next speaker is Chris Oostenbrink from Boku Vienna, and he's the head of the Department of Material Sciences and Process Engineering. And he'll be talking to us about AEDS.
Thank you. I think I'm hooked up.
Sorry.
Thank you very much for the introduction and for the opportunity to show a bit of our work. This is the first presentation I give with our new Boku University corporate design. So let's see where this goes wrong. First, the thing needs to wake up. Yes, so I'd like to start with this very, very old slide. I've been using this for 20 years already, and in fact, when I showed this at the 2019 Göttingen meeting, someone posted a picture just of the current speaker on Twitter, and half an hour later I had an email from a good friend of mine from Wollongong in Australia saying, Chris, are you still using that slide? So I think this is for Haibo. I'll show this slide again, because I think it's very nice. We've seen already some flavors of it today in this meeting. What I'm comparing here is the conformational space, and now I just need to find my pointer, there it is. The conformational space between two compounds which you would like to calculate the free energy difference between. And the Zwanzig equation, bar, whatever, it depends on having overlap. And very often we don't have overlap, and that's why these calculations don't work immediately, and then we introduce intermediates. And for a number of years, we've been working on alternatives to including these intermediates, multi-state kind of methods, where you try to design a molecule that by itself samples a broader phase space and has overlap with multiple real molecules. So a reference state in orange here that is that shows basically overlap with the two, so that you can, it's by itself an unphysical molecule, but it can actually be used to connect the real molecules that you're interested in. And then maybe there are more than two compounds that you could do, so that's where the efficiency then comes in, that you could do multiple compounds. So I like to, in my lectures, I like to show these kind of pictures where we're usually gradually changing one compound into another in the free state and in the protein-bound state, and I compare that to changing a chimpanzee to a more athletic version of myself. And then what we're now doing is we're using an unphysical intermediate state to connect the two ones, and we only simulate the states in the middle in order to speed up the simulations. And this is an example from a number of years ago where we had worked with collaborators from Denmark. They were interested in the glutamate receptor. It was a very small series, but I think it's a nice example. There's two molecules bound in the interface of the glutamate receptor here. And they had a series of differently fluorinated compounds here with just the substitution pattern on that side. They had ITC data, and we used that to compare the different methods. So we did thermodynamic integration from one compound to all the others. So these is pairwise. Each of them were done with about 14 lambda values with just 1 nanosecond per lambda. And we did these reference state simulations where we had a weird molecule where the fluorines were there, but not really. So what we do there is we use soft core potentials on the fluorine atoms, which means that they sample conformations where things bump into it, so they're really there. But the energy, the Lennard-Jones curve now goes to a finite value, and that means that from time to time, other atoms can overlap with it. They can show overlap. And that means that I sample both conformations that are relevant for the case where the fluorine is a fluorine, and I sample conformations which are relevant for the case where the fluorine would be a hydrogen or would not be there at all. And then we did one simulation here just of 10 nanoseconds of this compound, and we can then calculate with just a one-step perturbation, we calculate the free energy to all of the end states, and we also can get the relative binding free energies between them out of that. And if you compare here, just some metrics, here are the different compounds, how well does it match with experiment? In this case, in TI, we got a root mean square error of 4.5 kilojoules per mole, and for the one-step perturbation, we got 2.5 kilojoules per mole. Mind, this is kilojoules per mole, so divide it by 4 if you want to know it in kilocalories per mole. But then we were thinking this is still a little bit inefficient, right? We're sampling some weird molecule, and in this picture already you see we're sampling a lot of that, most of the time actually maybe not where we want to be, not really where the molecules want to be. So what you would want to do is sample a state where you have overlap, where you make sure that you really have overlap between them. So you are, ideally would sample exactly the phase space of compounds A and compounds B. And this was something that was done then by Clara Christ, also a number of years ago, and it was the birth of enveloping distribution sampling, where we say, well, the probability distribution of my orange state should be the sum of the probabilities of the two individual states, and then I can back construct what a Hamiltonian could look like. So I can create a Hamiltonian that should sample exactly the overlap between my different real states that I'm interested in. That doesn't work immediately because you still want to sample them sort of equally. You want to make sure that you really spend time in both of those samples. So then we need to introduce an offset parameter that gives a bigger weight to some of the compounds so that they actually get sampled equally in our simulation. So ideally, you would sample each of them for 50% of the time if it's 2 or an equal amount. And this was done in 2000. So Clara did this in 2007 already. What we now added to that is that we accelerate the transitions between them. So what we're trying here, a problem with EDS is still that you have two minima, you have two energy minima, and you sample them maybe equally, but there could be a big barrier in between. And then Clara introduced a parameter S to smoothen it, but they also shift the minima. So by using now the tools of accelerated MD, slightly reformulated here, but in principle it's the same. We take our EDS Hamiltonian and we accelerate it by adding a boosting potential that depends on where you are. And then we get an accelerated Hamiltonian that maintains the minima. So now we are sure that the minima of my mixed Hamiltonian are still at the places where my real molecules want to be. So that's quite essential there. So we did this in 2018. We tried it on a number of different cases. And one of them was this glutamate receptor again that we saw before. So we see the same numbers as before. And then with accelerated EDS, well, we get a very, very similar root mean square error. We get a very similar performance. So that seems to, at least on this very small test case, seems to work nicely. So that was very promising. And then we said, let's try to do this on a more complex case, like 5 compounds with just fluorines is maybe not so exciting. So let's do this on another target that has been tested well before. And this is the PNMT, the phenylethanolamine N-methyltransferase PNMT data set where we have 10 compounds that now have quite bigger differences. I mean, it's still R groups, of course, but there are different groups that are disappearing on both sides of the molecules. And Jan, who is actually here at the audience, he did that, and we do need to do a search run. I didn't mention that explicitly yet, but we need to search for these offset parameters such that we ensure that we get the same equal sampling of all our compounds. So we did a 100 nanosecond parameter search simulation and then a 200 nanoseconds AEDS production simulation such that we can incorporate these 10 compounds in a single simulation. Now that was a bit of a challenge because we included, I jumped too fast, we included also the known non-binder, so a compound that is known to bind very rather badly, and it has a negative charge. So it's a charge change compared to all the other compounds, and it has a binding affinity of 15 kilojoules per mole, where the other ones are around 40 kilojoules per mole, if I remember correctly. And what we saw in the simulation, that probably due to forcing now with our offsets to that this compound that doesn't want to be there, forcing it to be there, I give it a bigger offset so that it's actually also 10% of the time I see that compound. And that can then lead to structural changes in the environment. So the cofactor here, it starts to move around. So you still need to look very carefully at your molecule of what is happening. We did a very weak distance restraint to make sure that the cofactor stays where it should, but that's of course a little bit unfortunate. It worked very well though. So here we compared the root mean square error of exactly the same system, same force field, same parameters, done by TI, by Alan Mark's group, done with EDS already by Serena Rineker in 2011, with the replica exchange version of EDS by Dominic Zietler, and Benjamin Ries was also working a lot with reads. And with our accelerated EDS approach. And you see that we get a similar kind of correlation. Things are scattered a bit, but we get a very decent root mean square error, which is nice because this is now really coming just from these single simulations of our reference states, the search and the production run. But then So the next step, we went to a very classical benchmark system, right? So the T4 lysozyme ELF99A mutant, which has always been surprisingly difficult for very regular free energy perturbations. And I remember when I was visiting San Francisco in 2006, that David Mobley was already struggling with this. And one of the culprits is that the valine 111 basically samples different conformations, and for different compounds needs to be in a different conformation. That's a slow transition, and that is a problem if you're doing a regular free energy perturbation, where you would need to sample that in every this equilibrium between the gauche and the transposes of the valine in each of your lambda values, right? So this was a challenge, and we have different compounds here, so we did through that at our AEDS method as well. And here we did very short simulations, so 10 nanoseconds of a search run in water. So we do our 10 compounds in water. We make a hybrid state so that they sample all these 10 states equally in water. Then we did a second 10 nanosecond search run where we only optimized the offset parameters in the protein to give the different weights to the different compounds. And then we just did 2 times 10 nanosecond production runs where we split it up. Either we did all compounds in a single run, or we tried whether whether things mattered or whether we could improve further if we do it in separate groups. So in orange is the most interesting one, where all the different compounds were in a single run. We get this kind of correlation, and we get an root mean square error again of only 2.7 kilojoules per mole. So very comparable, very short runs, and it's very nice to see is indeed that you can also capture these trends. The nice thing of doing something like this in a single simulation is that we do now one long simulation where our valine has time to rotate, basically. It has the time to do that. It is just in these 10 nanoseconds, it does rotate. And what you can also then reweigh, you can look a little bit at which compound now prefers which conformation of the valine 111. So the bigger compounds, they are mostly in gauche, and if you go to the smaller compounds, the trans conformations become more relevant. So we can also capture these trends in the orthogonal degrees of freedom. All right, so that's also, that was very nice. But then thinking back to this situation where we had the PNMT, where we have an unfavorable molecule, we force it to be in the protein, and thereby we are disrupting our active site a little bit. And then we thought about, well, maybe we should actually use that information, right? If the protein doesn't want to see this ligand, it's probably not a very good binder. So what Oriol then did in my group was he said, well, maybe we can just skip this search run in the protein. If we just do our search in the water, so in water I sample each of my 11 compounds here, I sample them all equally. And if I now just take those parameters and put them in the protein, then the protein will tell me which molecules it prefers to see, which molecules would it prefer to bind. So we use exactly the parameters from the water, and this search run in water is usually very simple. And if we see the compound more than the 10% we see it in water, then it likes to be there. If we see it less than 10% of the time, then it doesn't like to be there, apparently. So that's very easily seen, and very nicely indeed when Oriol did that. If we use the parameters optimized for water and we put them in, we only sample these 3 compounds. So we very quickly identify only the 3 compounds that are the best binders, and that's what we want to know, right? I should have known about this best ranking score that was introduced by Chris Bailey yesterday. I think it would work quite well here, at least. Considering that we identify the 3 best compounds. For those 3 best compounds, we can still calculate their relative binding affinities as well. Well, that's not so very relevant because they're all in the same range as well, but it was nice to see that that also worked. So we tried this also again on our PNMT example, the one where it was where we had this disruption of the protein if we forced a non-binding compound in there, and there Oriol went a little bit further because he was also working on Gaussian accelerated MD for just the MD. So we use this idea, we optimize our parameters in water, and then we put them in the protein. And we do 2 kinds of simulations. We use just the optimal ADS parameters in water with a normal simulation, or we add a Gaussian accelerated MD on all the other degrees of freedom. So not the EDS particles, but the protein is under a small acceleration as well. And then in water, if we do that, so the water could also be accelerated, then we indeed can get a decent equal sampling range for these 10 compounds. You would expect 10%, but by doing a quick search, we can get something to 7 to 13% of them. And if we put those in the protein, then very nicely what we can see indeed, again, this is a bit of a difficult table maybe. Here's the experimental binding affinities. And if you look at the deepest ones, like the ones that bind most strongly, those are the ones that we sample in the simulation. Yeah, so the green ones in the green bars, those are the ones that we observe in the simulation. This works for the straightforward AEDS, and it works for the ones where the additional Gaussian accelerated MD is on the surroundings. So again, only the best binders are sampled, and then all the ones that we sample at least and a little bit, the ones that contribute at least 500 times to the free energies, we try to still quantify them, and we still have an RMS error of about 4 kilojoules per mole, so about 1 kcal per mole. So that even works as well. Now that was very nice, and you can also expand this. You can use the free energies or the AEDS method more as a chemostat, as a method to determine whether molecules like to be there. So this is what I would quickly like to show still, where we use a water molecule that we now sample in bulk water to be 50% of the time a real water molecule, and 50% of the time it goes to a dummy state. Yeah. From such a simulation, you can then calculate the solvation free energy of just a single water molecule in water. That's not very, very interesting, but we could apply this to a set of six ligand protein pairs where experimentally water molecules had been seen to play a role. So there's this Wall and Smiesko created this set and described that set, or they collected the set basically. And there's always two compounds where in one of them experimentally there is seen, in the crystal structure, there's a water molecule seen, and for the other compound that is very similar, it is displaced by some part of the ligand. That's very nice, because that allows us to test our flickering water molecule. So we have this water molecule that likes to be there or not likes to be there. In water, it's about 50-50. If we put this now in a protein, then we see that in this first case, for example, when the water should be there, indeed, AEDS agrees it's 100% of the time sampled. If it should not be there, it's only 5% of the time sampled. And for each of these pairs, this works reasonably well. For some of them, it's a little bit more It's a bit more challenging. Here it's 40 to 0.2. It turns out that this molecule, actually the ligand, does a conformational change that was possibly not to be observed according to the crystal structure. But I want to draw your attention still to this one that Anita already mentioned on Monday shortly. This is the Woodhead pair, where experimentally there would be 2 or 0 water molecules seen. And what we noticed is if we, and I think Anita mentioned that already, if we did this AEDS waters, we always saw, now it's a bit silly that it overlaps with my name there, but we saw one water molecule that was really never there, and the second water molecule that was not observed in the crystal structure was actually there for 100% of the time. So it was all the time there. So we didn't go from 2 to 0. Our AEDS simulation suggested that we go from 2 to 1. Then this was also a slide that already Anita shortly showed. We have the experimental relative binding affinity between the two Woodhead compounds. If we force there to be always 2 waters, it goes wrong. If we always force to be 0 waters, it goes wrong. If we do 2 waters in one state and 0 waters in the other state, and we do that also in the alchemical process, it still goes wrong. And if we adhere to our AEDS predictions, where we have 2 waters for compound A and 1 water for compound B, then we get very close to the experimental value. So that is a suggestion maybe that at least in our force field, this 1 water molecule should really be there. And what you see here is that we then combine this not only with a multi-site EDS, but also with TI. So here we do a thermodynamic integration, and as lambda changes, we change the molecule. So you see that the molecule changes, and at the same time, the flickering water molecule can change its behavior. So you saw at the beginning of the movie that the water molecule was flickering relatively often there. That's the blue curve here, so it was seen very often. And at the end of the simulation, it actually doesn't sample anymore, so the water disappears. And the nice thing of this whole construction like this is that we get also all the free energies out. So we can quantify how happy is the water there. Does it like to adjust? Does it like to stay there? Where does it go? How does it go away? And how can we incorporate that in our binding free energy calculations? And both, if we do it just with TI and we explicitly say this water needs to be removed, and we get 7 kilojoules per mole, which should be 8.4. If we do it with an AEDS water, we still get 7 kilojoules per mole. So that seems to be very consistent and lead to a very similar result. All right, let me just try to wrap that up. I try to give you some examples about one-step perturbation approaches where we're simulating an unphysical reference state to obtain real free energies. You need to choose your reference state carefully, and using AEDS allows you to do many things like that. And what I'm very excited about is that we can sample also multiple states in a single simulation. We can sample orthogonal degrees of freedom, and we can use it in a sort of grand canonical way as a chemostat that we can do a virtual screening to identify at least the best binder, which is very often what we would like to know. Thank you very much. These are some acknowledgements. So the people involved in this work were Jan Pertold here in the audience, and Oriel took over from him, some collaborators and some funding agencies, and part of our new corporate design. I say merci beaucoup.
Any questions?
Hi. I see that some of your molecules were sulfonamides. Do you think that the force field, are you comfortable that you're modeling them correctly? Because a lot of people have found that sulfonamides are particularly difficult to represent in a force field.
Yeah. That's true. In the case where we used them, we basically just took the benchmarks that were done by Alan Mark, so I'll just put the blame on him. We were mostly concerned here about comparing to the previous calculations. Nice that the correlation with experiment was nice. For the methodological point of view, from a methodological point of view, it was more relevant that we got similar results to the TI calculations and the earlier EDS calculations, basically. But so we didn't look carefully at whether the parameters were really good. We just took what was done previously to be able to compare to those. But I'm fully with you that I would not put my hand in the fire for the parameters. Yeah.
Any other questions?
Hi. How scalable do you think this is for free energy calculations of ligands? Because I assume that if you start introducing more ligands, you run into some issues.
Yeah, so we started calling this a virtual screening mode of EDS. We should not do that in principle because we're not going to go to thousands or 10,000s of compounds, because you still do need to do this search run in water where you need to find you need to get roughly equal sampling of all your states. If you have 100 compounds, that will be difficult to obtain, I think. But that's about also the limit where I really see that it goes. So I think it's rather at the stage where you have a small set, or you could do multiple of these small sets where you combine your series and then you identify the bests of those, and then you can connect those still with a perturbation, nor with a regular perturbation. Yeah.
Could we get another round of applause for Chris?
Thank you.